Hello everyone, can you hear me?
Yes, sir.
So let me share my screen. By the way, tomorrow I may not conduct live lecture. So just a second. So if you have any doubts for the internal, then you may want to ask today, or you can of course message or email. That is always there. Okay. Okay, so today we will talk about likelihood ratio test for equality of dispersion matrices. Now again, first question is, why do we need such a test? So in Hotelling T-square test as well as in MANOVA, if you have heard the lectures, we have an assumption that the dispersion matrices are equal. We have similar assumptions in univariate setup, right? In the t-test also we assume that the two dispersion matrices are equal. In ANOVA also we assume that all the populations have common dispersion, not matrix, we have common variance, and same thing is carried forward for these tests. So in Hotelling T-square as well as in MANOVA, we assume equality of dispersion matrices. So when we are talking about equality of dispersion matrices as an assumption, we need to develop a test for checking that assumption. Okay, so today we will do that, and we will directly do for K. So of course two populations would be a subcase of it. Okay, and I'll follow the same pattern. I won't derive the actual likelihood. Now you know it finally boils down to the determinant of the estimate of sigma under H naught and estimate of sigma under H, the overall setup. Okay, so let me first write down. So I think this is fourth likelihood ratio test that we are considering. So equality of dispersion matrices of K multivariate populations, multivariate normal populations of course, K multivariate normal populations. Okay, so what is my H naught? Wait a second, someone has joined it seems. Yeah. Okay, so I have NP mu 1 sigma 1, NP mu 2 sigma 2, NP mu k sigma k, sk different populations. Okay, and of course we are going to assume that they are independent. Okay, and my null hypothesis is sigma 1 equal to sigma 2 equal to sigma k. This is my null hypothesis. Okay, so what will be the null parameter space and overall parameter space? Overall parameter space still remains the same. You have some p variate vector mu, p variate variance coincidence matrix sigma, mu belongs to Rp, sigma p cross p is a symmetric non-negative definite matrix. Correct? Okay, symmetric non-negative definite matrix. And under H naught, I don't have any constraint on mu, so mu remains as it is. Sigma becomes, wait. Does anyone see some mistake here? Yes. Can anyone spot some mistake here?
We have K sigma.
Correct. And we have K mu's. So I have to write mu I sigma I. Every mu I is in RP. Every sigma I is this. And this is true for I going from 1 to up to K. I am not talking about single mu or single sigma now. Correct. I am talking about K mu's and K sigmas. And under H naught what I would have? I would again have mu I, but my sigma would be common. I won't have I here. Okay. So I would have mu I belonging to RP and sigma is one matrix. Instead of K different matrices, I'll have one matrix. Is it okay? Symmetric, non-negative definite matrix. What I have is K different populations and each population is p-variate. From first population I am supposed to have n1 observations. So let me call them x11, x12 up to x1n1, n1. These are coming from np mu1 sigma 1. Okay. These are in your familiar terms IID NP mu1 sigma 1. Mu1 is p cross 1, sigma 1 is p cross p, and each of these observations is p cross 1. Okay. So this x11, x12, x1n1 is a sample of size n1 coming from p-variate normal distribution with mean mu1, variance covariance matrix sigma 1. Is this line okay?
Yes.
Similarly, I would have x21, x22, x2n2. These are IID, NP, mu2, sigma 2. So each of these is again a p cross 1 vector, but they are now coming from second p-variate normal population and the number of observations can be different. Okay. Similarly, xk1, xk2, xk and k are IID, NP, mu k, sigma k. Okay. Got it?
Yes, ma'am.
Now let me write down likelihood for first population. L1. L1 is 1 upon 2 pi raised to np by 2, 1 upon determinant of sigma 1 raised to n by 2, e raised to minus half sum over. Now 1 is constant, mu 1 sigma 1 is there, so sum over, let me write j going from 1 to n1 x1j minus mu 1 prime sigma 1 inverse x11j minus mu 1. Is it okay?
N1. Yes.
Oh, here n1, correct. Yes, thank you. Here also n1, here also n1. 2 pi raised to n1 p by 2, 1 upon sigma 1 raised to n1 by 2, e raised to minus half, sum over j going from 1 to n1 because this 1 to n1 and x1 part is there, minus mu 1 prime sigma inverse x1j minus mu 1. This is likelihood for the first population. Everyone with me so far? कुणीतरी दुसऱ्याने बोला आता.
Yes, ma'am.
Okay. So now when I want to write joint likelihood, this right now I have sum over j, but when I write joint likelihood, this 1 is also going to vary because I'll have to put 1, 2, 3 up to k and take product over that. So joint likelihood will be product over I going from 1 to k 1 upon 2 pi raised to NI p by 2 1 upon determinant of sigma I. So here also I have not highlighted that, raised to Ni by 2 e raised to minus half sum over j going from 1 to Ni x I j minus mu I prime sigma inverse x I j minus mu I. Okay so far?
Yes, ma'am.
Now log likelihood. So when I take log, it will be sum over I going from 1 to k NIP by 2 log of 2 pi with minus sign, then minus Ni by 2 log of determinant of sigma I minus half sum over j going from 1 to Ni x I j minus mu I prime sigma inverse x I j minus mu I. Okay.
Sigma I related with sigma
Yes,
I.
yes. Sorry. Sigma I inverse. Okay.
Yes.
Okay. And now if I differentiate with respect to say sigma 1. Okay. If I differentiate with respect to sigma 1, this part is anyway, whatever you differentiate with respect to, this is anyway going to vanish. But when I differentiate with respect to sigma 1, then from this part, only the term containing sigma 1 would be differentiated. I am saying I going from 1 to k. So it can have sigma 2, sigma 3, sigma 4, sigma 5. But all those terms would vanish when I differentiate with respect to sigma 1, because the populations are assumed to be independent, and hence sigma 1, sigma 2 are also independent of each other. Okay. So when I differentiate with respect to sigma 1, I have to worry about derivative with respect to sigma 1 of minus n1 by 2 log of determinant of sigma 1 minus half sum over j going from 1 to n1 x 1j minus mu 1 prime sigma 1 inverse x 1j minus mu 1. I don't need to worry about any other term, because all the other terms are going to vanish. Is it okay?
Yes, ma'am.
What about others? Is everyone okay with whatever is happening here?
Yes, ma'am.
Okay. So now, and I know that this, okay, someone has joined. Wow, the number is decreasing instead of increasing. Okay. So, this part now we know is our usual multivariate log likelihood. So we have already solved this when we were trying to find MLE, and we would get sigma 1 hat as S1 upon N1, where S1 is CSSP matrix computed from first sample only, sample coming from first population. So that will actually be sum over j going from 1 to n1 x 1j minus mu 1 into x1j minus mu1 prime. This is our formula for CSSP matrix. Correct? In fact, you have a simplified version also. I can write S1 as sum over j going from 1 to n1 x1j minus, I want to write simplified form, correct? So x1j prime minus n1 times mu1 prime. This is, I think, the simplified form. If you have notes from maximum likelihood estimation part of multivariate normal. Okay. So in general, when we are in the overall setup, not under H0, in the overall setup, I will have sigma I hat as SI, that is CSSP matrix of that corresponding sample, divided by the corresponding sample size. Okay. Okay so far? Under no restriction. No restriction means overall setup. Whereas now when I go to H0, what is the change that is going to occur? When I try to find something under H0, instead of sigma 1, now I would have sigma. Okay, so let me write down. Let me write down log likelihood under H0. So this portion, can I just copy and edit? I don't know. Let me write again. Okay. So under H0, my log likelihood is going to be sum over I going from 1 to ni stays minus ni p by 2 log of 2 pi minus ni by 2 log of determinant of sigma. Now I will have a common sigma. Okay. Now I will have a common sigma minus half sum over j going from 1 to ni x I j minus mu I prime sigma inverse x I j minus mu I. Okay. I have xij minus mu I prime sigma inverse xij minus mu I. So sigma is common. So when I differentiate with respect to common sigma, all these terms would remain. First would go, of course, but I would have sum over I going from 1 to ni. Now the sum would remain, and then I have to worry about derivative with respect to sigma of minus ni by 2 log of sigma minus half sum over j going from 1 to ni xij minus mu I prime sigma inverse xij minus mu I. Okay, square bracket also closed. Are you getting?
Yes, ma'am.
So what would happen? Now see, this is similar to your pooled variance in t-test. Now because I still have mu i's here, so mu is not common. So I can't say compute overall CSSP matrix and that would give you that would help you in getting MLE. That won't be the case because I have individual mu I here. Their estimate, they would be replaced by xi bars. So xi bars are sample means of the respective populations. They are not the common means. Okay, and my H0 doesn't say anything about the common mean. So it says that means can still stay different. Okay, so I would have terms like xij minus xi bar into xij minus xi bar prime sort of thing. So for each I will have to take its own SI, its own CSSP matrix, and then we have to take their average. Okay, so you can try this actual estimation also So under H naught, the common estimate turns out to be S1 plus S2 plus Sk divided by N1 plus N2 plus Nk. Okay, the common estimate of sigma turns out to be this. This is exactly similar to your pooled variance, correct? Okay, and my likelihood ratio test statistic would again be determinant of sigma hat under overall setup upon determinant of sigma hat under null setup divide raised to n by 2. Okay, so under overall setup I would have S1 by N1, S2 by N2, correct? Because I'll have individual sigmas. I don't have a common sigma. And Sk by Nk divided by, this is sigma naught hat, something like this. And we will not have this common n by 2, so we'll have to worry about individual n by 2s. So homework is to find out this lambda. What would be lambda? It will be something of this sort, but of course there are many mistakes because I have to worry about n1, n2, etc. Okay, so homework is to come up with this test statistic. Is it clear?
Yes.
Okay. Now, only one small test is remaining. So let me cover that. So we talked about equality of means in Hotelling T-square and MANOVA. We talked about equality of variances in LRT. What to do if we want to check equality of both means as well as variances? Okay, so equality of mean vectors as well as dispersion matrices. So what to do under such setup? Means what? My H naught is mu1 equal to mu2 equal to mu k and sigma 1 equal to sigma 2 equal to sigma k. Okay, mu1 equal to mu2 equal to mu k and sigma 1 equal to sigma 2 equal to sigma k. That is my H naught. So what I'll do is I will call this as first H naught. Then I'll construct second H naught as mu1 equal to mu2 equal to mu k given sigma 1 equal to sigma 2. So here you don't have to, so the difference between these two is under the first H naught I want mu i's and sigma i's both to be equal, whereas under second H naught I am already assuming that sigma i's are equal and I am checking only for mu i's, and the third H naught is only equality of variances, sigma 1, sigma 2, sigma k, and we are not talking anything about mean. Why am I doing this? Why am I introducing additional H naughts? You will see in a minute. We have already derived different tests. So can we use those different tests directly without going to the computing from scratch, writing down likelihood, etc. for testing this current null hypothesis? Okay. So let me discuss parameter spaces. So for first, the parameter space is single mu and single sigma, correct? Because all mu i's are supposed to be same, all sigmas are supposed to be same. So single mu, single sigma. For second null hypothesis, what is the parameter space? Actually, technically for second null hypothesis also the parameter space is same, because for they are again having sigmas are given to be same, so it is common, and mu's are supposed to be same under null hypothesis, so mu is common. And the third parameter space that I'll construct is only sigmas are equal. Okay, so mu i's can be different. So mu I, sigma, mu I belongs to RP, sigma is common. So that part remains. And one overall parameter space is where nothing is equal. Okay, so mu i's are different, sigma i's are different. So overall parameter space is mu I, sigma I. Each mu I belongs to RP. Each sigma I is P cross P. Symmetric, positive definite matrix, etc. etc. Okay. Now, likelihood ratio test for testing the first null hypothesis would be supremum over theta belonging to the first parameter space, because that is my null of log likelihood, of likelihood, divided by supremum of theta in overall parameter space. Correct? Overall parameter space means this. This would be my likelihood ratio test for the first hypothesis. Now for second hypothesis, what do I have? Sigmas are given to be equal. For the second null hypothesis, sigmas are given to be equal. So for second hypothesis, null parameter space is still the same. The first, this script theta not 1, whereas overall parameter space would be this. Mu is different. Which one? Yeah, this one, third one. Okay, this one. Mu is different, but sigma is still common because it is given that sigma is common. So even in the overall parameter setup, sigma is common because that is not part of the hypothesis, that is part of the assumption. So I'll have supremum theta belonging to script, this remains the same, and what is happening? Okay, anyway, so I'll have supremum theta belonging to h naught, and what is the 3? Correct, because mu's can be different. In the overall parameter space, mu's can be different, but sigma has to be common. Okay, this is test for second hypothesis. And for third hypothesis, what is overall and what is this? For third hypothesis, null is this, that mu's can be different and sigma has to be common, and overall space has to be this, script theta. Okay, so my lambda 3 would be supremum theta belonging to script theta 3 divided by supremum theta belonging to script theta. Okay, because for third, null space is actually this one. Sigma is common and mu's can be different, and overall space is overall space. Now, can you see some relationship between lambdas? Can you see some relationship between these three lambdas?
Yes, ma'am.
What is the relationship?
Lambda 2 is equal to lambda 1 by lambda 3.
Lambda 1 is equal to lambda 2 into lambda 3. I will write in terms of lambda 1. Why? You're right. You told just by shifting this. So I would write in terms of lambda 1 because lambda 1 is actually currently my hypothesis of interest. I want to test equality of mean as well as mean vectors as well as dispersion matrices together. So I can do that via lambda 2 into lambda 3. So I can get this test statistic by multiplying lambda 2 and lambda 3. But why should I compute two different test statistics? Why not directly compute lambda 1? So the interesting point is these test statistics are not new. What is lambda 2? this lambda 2 test statistic is actually your MANOVA test statistic, because you are assuming that sigmas are same and you are checking for equality of mean. So this lambda 2 is nothing but your lambda 2 coming from MANOVA, and lambda 3 is coming from the earlier test, equality of K dispersion matrices. So the test that we just now derived. Okay. So if you have already carried out these two tests, then you can simply take product of these and get lambda 1. Okay. Now I have two homeworks for you. Let me write those and then we'll stop. So homework, what would be homework? Can you guess? Yes? What would be homework? Can you guess? Compute the degrees of freedom for the two tests that we studied today. Compute degrees of freedom for test number 4 and 5. I have not done that, because now we have enough practice of computing degrees of freedom, so I have left it for you. So do try that. Okay. Is it clear?
Yes, ma'am.
So this finishes our discussion on testing of hypothesis. We won't have any more tests. Okay. So let me stop here. Thank you.